Okay, so hopefully my slides are visible. Yeah, so welcome to live session 11. So today again we are going to start with some problems followed by some discussion of total synthesis, natural product total synthesis. So let's get started. So for today, this is our first problem. So today's problems are mainly based on kind of achiral or chirality related problems and achiral synthesis or stereoselective synthesis. So for today's problem, the first is they are asking a optically active alcohol. The molecular formula is given, is oxidized by Jones reagent. So I hope all of you know Jones reagent. So we have probably multiple times discussed about this many oxidating reagents. So Jones reagent is one of them actually. And they are asking oxidized by Jones reagent to an optically inactive or achiral. So they are asking the if we oxidize a molecule and with this particular reagent. So what is Jones reagent? So it is nothing but CrO3 in acidic condition like this. Jones reaction this is just Jones reaction condition for the oxidation of alcohol. So it oxidizes alcohol to its corresponding keto or aldehyde molecule. They are asking if we oxidize and the molecule would be achiral or optically inactive. So let's look at the option. So for the first case, if we do oxidation, so one thing to notice here, we have two chiral centers. So this molecule is chiral because it contains two chiral centers, and when it become achiral, when there are no uh, chiral center in the molecule will be present, then it will be achiral. So when we do the oxidation for this particular molecule, so this particular alcohol will be converted to its corresponding keto, but this center would be absolutely unaffected by that, and it. So after oxidation, you can see one chiral center still remains and in this molecule. So this molecule again, this should be a chiral molecule, not a chiral or optically inactive. So A cannot be the right answer. So with oxidation, you are clearly seeing. So this part, this alcohol part, this particular chiral center is destroyed due to oxidation. So what oxidation do? Oxidation do? It just kills this particular chirality and make this particular chiral center to a chiral center. Now for the B, for this molecule again, it contains three chiral centers actually. So again, if we do the oxidation here, one chiral center would be absolutely destroyed, but other two would be unaffected because they are just carbon-carbon bonds. It would not be should not be affected by this Jones reagent, chromium trioxide based. So again you can see this after oxidation one chiral center is destroyed, but it has two chiral centers. So again after oxidation this molecule is a chiral molecule. Obviously it cannot be a chiral one, but look at for this case, for this kind of molecule here only one chiral center is present in the molecule, because this center 2 CH3, so it cannot be a chiral center. So this is a chiral molecule with one chiral center. So when we do the oxidation for this case, as we have just one chiral center, it would be destroyed, and that would lead to a formation of a chiral molecule, because in this particular case there is no chiral center, so it is an achiral molecule. So C would be our right answer, so what they have asked. For D case again you can see it contains two chiral center, but the Jones reagent can only oxidize the alcohol part, other alkyl part would be remaining intact. So one chiral center is still there, so it is a chiral molecule. So in that way, it is this is how the reagent chemistry and stereochemistry mix problem. This one, and you can easily solve this kind of things. So now moving to the next problem. So they are asking what would be the major product in this particular event, if this particular event takes place. So at first what they are asking, they are using B2H6, means just boron based reduction, and then they are asking with acidic condition applied. So I hope you know that the reduction, the selectivity or chemoselectivity of reducing reagent. So this BH3 selectively can only reduce the acids, not esters. So this is a kind of, you can say, selective chemoselective um, reducing agent. So today there is some network issue actually, that's why sometime it got disconnected, so bear with me. So this BH3 only can reduce the acid part, not ester part. So BH3 is quite selective regarding that. So after first reduction, let's see. So the product that we are going to get is in the reduced version of acid, which is alcohol. CH2 CH2 OH, and here we have just external. Okay, so here it will be above. Because we are turning this, so that's why this. So, but easily you can do that by RS nomenclature actually. So let's look at, so 1 2 3. So it's going this direction, but as hydrogen is above, it is S. Now look at this. So 1 2 3, it is S, and here nothing to worry because hydrogen is below. So that's how you can easily after this type of rotation, you just can quickly check if you have correctly assigned the above below groups with quick RS nomenclature. You can do that. So now after that, when we do the H plus treatment, it's nothing, just this me part or this part would get protonated, and it would help to remove the one methanol unit from the system to from this particular lactone type moiety. So that's the role of H plus, nothing else. So after that, you generate this kind of moiety. So it's already we have assigned its S, and here it is. Then we can easily assign this one. One should be this part 2 and 3. So this kind of in this way we can easily assign, but here with you can just directly correlate with the from the electron moiety, and it's just matching with it. And here you can see this particular chiral is reversed. That's why it is not correct again. This is reversed, and for this case both chiral are reversed. So that's why they are quite wrong regarding that, and they would be your answer. Now moving to the next problem. Mm, Again, it's very again quite easier one. Just one SN to elimination type thing. So let's see. So sodium hydride is it's act as just a base, not a nucleophile. So why I have I think I have discussed. So why this H minus cannot act as a nucleophile, because the its H minus, Na plus and H minus, it's only have S orbital, and S orbital is, as it is completely spherical, so there is no such directional property. So that's why it cannot act as nucleophile. But for case of, let's say, this kind of cases, so as these hydrides are actually bonded with aluminium, so these particular hydrides, they have actually some they are hybrid orbitals, means they are hybridized orbitals. So let's if we do the vacancy that thing, so it would be some SPN, something like that. So that's why they can show directional property, and it can act as nucleophile. So that's why sodium hydride can only act as a base. So after sodium hydride acts as a base, what it do, it can extract any of the protons of these primary alcohols. So after abstracts of proton. So it have two probability actually. It can abstract proton from this primary alcohol or the other one. So as soon as this proton abstraction happens, this particular chromosome is very much electrophilic in nature, and this SN2 type attack would be happening, and it would form its corresponding cyclic ethers. So for this case, it would form a four-member ring, and as it is an SN2, so this O minus would be approaching from above the side. So for this case, this should be this, and for this case, it would be just a epoxide. So it's not above, so above would be this. Near the same side it would be, so to explain, so it would be above. Anyway, this is not a chiral center, so not a issue. So you can see with that we can just eliminate A and D, because they are not matching with the assigned stereochemistry, because stereochemistry is important because we are doing the SN2, and the inversion of chirality should be there. So now we have two options between B and C. So between this type of oxytanes and epoxides are turned out to be a thermodynamically favored product. So stability of this is much more than that, and that's why this particular attack is more favorable than this, and kinetically also this kind of attack is more favorable. Why? Because you can see, so from this particular sp2 from this particular electrophilic center, the nucleophile is just one carbon away, but for this case the nucleophile is two carbon away. So probability of the right configuration to attack of this particular thing is quite high than this. So that's why the kinetic also kinetic, if we think kinetically, then also this particular product is favored. So in that way, the formation of epoxides is very much faster compared to your oxygen type molecules. So that's why the product would be the epoxide, not oxygen. Now for the next case, they are asking about the correct retrosynthetic pathway to form this kind of molecule. So again, it's just a stereochemistry based question. So in the product, you can see the hydroxy group is above, and the methyl group is below. So we need to just maintain this thing, and so here for all cases, not all cases, for these two cases, for three cases, the nucleophile is this Gilman reagent, which is copper lithium type, so that the nucleophile just it makes the nucleophile little softer due to presence of this copper, and it is very much harder nucleophile. So that's the only difference between these Gilman type reagents and methyl lithium reagents. And here you can see, if we do the methyl attack from in this case, so here you can see, uh, here again we need to do the SN2 attack. So if SN2 attack is happening, it should be happen from the below the face, because the epoxide ring is above the brain. So for SN2, the nucleophile should be below for both the cases. So both these two attacks are possible, and so the two possible attacks, after the two possible attacks, one product would be here methyl, and here OH, and another product would be here OH and here methyl. So that's the two things. And if you do the RS, I think it should to be the consumer, I guess. Let's do the RS nomenclature. So is one, so it would be R. 1, 2, 3, R. 1, 2, 3. It is sorry. So that's how things should be, and you can see you generate two enantiomers actually. So so one of the enantiomer you would be generating is this one, and it is actually matching with this. And for the second case, let's see. So again, two possible attacks are there, and as it is also an SN2. So one case it will be like this, and another case the another case which would be below over here, and it will be the above. So now just check the stereochemistry of OH. You see that it would not be matching, and so here I think the right answer should be this A and B actually. Hydrogen is above. RR should be our product. So here again, so these two are actually same compounds after if we do the just 180-degree rotation. So that's why A and B both could be the A and B both could be the right answer, because if approach of methyl is equally possible for both these two centers. So anyway, we are going to generate one of the enantiomer actually, RR or the another one. So that's how we can determine the RS nomenclature of the compound and just correlate with the given one. And for this case it is completely relevant, because with this you are going to have a 1-2 attack which would from uh, this type of molecule which is not correlated with the given product that is they have asked. And for this case again you can see Gilman reagent, it would do the 1,4 addition due to its software center, and it is a soft nucleophile soft matching, and it would generate this type of molecule. Again it is not related to that, so the accepted answer should be A or B. And for the next case, so they are asking the again which the electrosynthetic pathway should be correct one. So it base, if we treat just the base over there, it would abstract this proton and it would do SN2 attack. And anyway this is not a chiral center, so no converse inver inversion of configuration issue are going to have. So this particular center it is not touched, again it is also not touched, so we should to be retained and it is matching, so that's how A would be the right answer. And for this case if we do this reaction, it would form a molecule like, if it can do the SN2, it would have a compound like this. But in general, we know for the four-member thing, the anti-conformation is quite strained and impossible to form. So probably you would see no reaction over for this kind of cases. And for this case, you can see. So this is the nipping group, and here we have this type of thing. So again, if this attack we need to do, it would form a four member ring, but again this would have to generate this kind of strained four member ring. Again it is quite impossible to form, and this kind of product did not exist actually. And for this case again it is quite related to this, and for this kind of, this is the product that we are going to form is just for remembering, and it would be just below. So antioxidant we are going to be forming if this reaction happens. So only synoxidine is kind of possible to form for this kind of substrate if or starting material if we use, so that's why they would be the right answer. And for this case, then they are asking which is the correct electrosynthetic path. So SN2 and OTS should be the leaving group, and so here what is the nucleophile? So I minus kind of thing would be the nucleophile, and let's say we can use this kind of salts, sodium iodide salts. So for this case, if we do the SN2 with I minus, so again inversion would be happening in this particular center as we are doing SN2. So here tertiary butyl, and here iodide will be above, but here you can see it is below, so it is not the right course option. For this case, it is above, so I minus should be from below, and from product should be like this. So this is our required product. So I am writing this way, but if you present this, you should always follow the chair configuration, and the butyl would always prefer to be in tutorial fashion. So this and here and two things are there. So OTS is like this, and for this case OTS is above. So again, it's kind of axial. Your living room remaining this axial from the attack is it is there again, and this kind of approach can easily eliminate that and from this molecule. And this kind of cases, so for this case, so we need to incorporate an iodide molecule here, and we need to do in chiral fashion. So it's quite hard, I would say, because what maximum we can do, we can generate a radical. So if we generate a radical, it always prefer to be this side over this. So in any other way, probably from this substrate to this conversion of this is quite difficult, and this should not be your right option. But so let's explore how, if we have this compound, how we can make this. So let's say at first we do uh, a CO2 treatment and make a, and we do a allylic oxidation over here. So other products are possible. So here also its incorporation you may see, but definitely this should be your one of the products could be forming, that would be this. So now we need to make this, or we need to reduce this molecule, and if we let's say we do the NaBH4 treatment, and we can make this molecule. But this anchoring of the this tertiary butyl, let's see if it can play any role or not. So it's like this. So it's would be the wrong confirmation. So tertiary butyl group is above, and here it's like this. So you can think that each approach of hydrate venous from here and here, which would be more favorable. So this kind of approach should be favorable, because it can, this particular have hydrate venous can face some strain with this tertiary butyl group, although it's in equatorial form. So the major product, we can say, if some amount of majority in the product formation would be there, that should be an alcohol which is axial, means it is above. So anyway, after and if the other and then uh, another isomer, that would be definitely be forming, we cannot control that, where this proton would be above. So there are many techniques to just difference or to separate this kind of two, these two, and let's say other reagent we can use, like if we do the CBS reduction, we can so CBS, I think so Coreboxy is this, but this famous reducing reagent that is available, and actually for this kind of cases, or with CBS, generally people got a high immensive selectivity, and SCBS and RCBS both are available in commercially, and if we use one of them, in the one of the CBS would give you your required which chemistry. If we need to make it above, it probably SCBS can do, and if we need below, RCBS can do that. So just you need to with CBS you have a model, and with that you just can on paper you easily solve according to your required product, which kind of product you are going to be needed. That's how the particular CBS S or R could be chosen. So in that way we can have a OH in our desired position. So let's see. So here the I minus we are needing in the what phase? Below phase. So if we have this OH in the above phase and we make it a living group, so let's say we did a mesylation MSCl. What is MSCl? It's nothing but this kind of thing, and when OSO2Me is there, it become a good living group. So that's the advantage of this particular reaction. So now we have OMSC. Now it's somehow we converted this molecule to this. Not actually it is done, because we have a double bond actually. So after that we need to do a hydrogen palladium charcoal reduction of this particular double bond to make it cyclohexane completely. So after that only we can do the iodide treatment and make this. So this is one of the cases, and that's how we can just make this particular molecule to this, provided SN2 reduction we can do that. So that's one of the way for this kind of system, but you already see that how much long it would be. So one step, two step, three step, four step. So if we want to do this particular transformation from this to this, it would require four step, whereas simply we can do from here to here. So that's the advantage of choosing this path or this retrosynthetic pathway B over C, because B would the C would require a long or many steps. And so one thing on another thing I want to discuss. So for this case we are just converting this molecule to, tertiary butyl group is there, and here we have above OH. So somehow with a few with three steps actually we are converting it to there to there. So first CO2 sodium dioxide based allylic oxidation, followed by hydrogen palladium based double bond reduction. This double bond can be reduced. Now here from we can use one particular reaction. You may remember this particular thing. So what it is called? It is just the Appel reaction conversion. So what it do? I hope all of you remember, but it's just quick, quickly I want to discuss. So with PPH3 treatment at first, so PPH3 at CI4 is there. So PPH3 at first attack one of the halogens and it would do this kind of thing. So now we have this particular molecule. Now here actually this OH can be deprotonated. So how it can be deprotonated? Because we in situ generate this and it is the basic nature. So minus can be generated. It can attack with it can attack phosphorus because of you can you know the strength of phosphorus oxygen bond. So when it attacks, so it's not a complex formation. It can directly remove that. So I minus is generated, and here we have generated this thing. Now just I minus we would attack in the one of the carbon atom. It would break the carbon oxygen bond and phosphine this phosphine phosphine oxide would be the byproduct that you would be forming, followed by this Ri. So and it is always an SN12. So which actually suits our this thing. So that's why I discussed the Apple reaction condition. So in the if here we do the Apple reaction, so the product that we would be getting would be iodide would be below and it would be above. So this can be one of your path if you want to make this to this. But anyway, here B is much easier, so that's why we have chosen that. Let's see how we can again do from this kind of species. So here it is just uh, multiple choice, so that's why we can choose. But let's say if you are asked here to here how you can, then you need to think. So that's why I'm just discussing things. So now again how we can do from here to here. So one of the easier way would be HI treatment, and it would actually generate quite a lot. So there would be very much less selectivity if we do this particular HI treatment, because one product would be this and here it is chiral center. So here we are getting two products and then here also iodide but two products. So probably here formation of this particular product would be 25% or less than that, because there are four possibilities. So it would be not a good path to do this kind of thing. So I am thinking if any good way is possible actually. And if we do the hydroboration oxidation, uh, that can have, so let's say we use 9 ppm. So I hope that you know the structure of 9 ppm. So this is 6, 1, 2, 3, 4, 5, 6. So this kind of thing is 9 ppm, and it would the due to huge bulkiness of the alkyl groups, it would try to form such a way that such a way that steric interaction of with tertiary butyl group would be absolutely minimized. That's it would obviously try. So then I think if we use that, so then there the boryl species would be there. So if here the steric interaction with the 1,3 interaction is would be greater, so there we can expect some selectivity of this molecule, and here from here just we can make it OH, then alcohol followed by so H2O2 treatment followed by oxidation, and we would again generate our previous precursor, which is this. So from here we can do the same three-step process. So it it can be one of the option if you want to make uh, this molecule from this one. So any better path I don't think seem to have from here to here. So that's all for the six problem. Anyway, that's these are we are discussing just to explore, but the most easier way to form this would be this option B. Now coming to this, again it would be very much easy because here you just see this particular center, because these two is almost fixed in all the cases. So here so in with base we and this kind of thing, so we are going to do just SN2 attack. So we need to have an hydroxide here, the hydroxide would be above, so that it would do the SN2 attack, and the halide would be the below, so that should be the right option. So for this case, the formed epoxide would be below, SOH is below the plane, so attack would be from the below the plane, so below epoxide would be formed. So here no such innovation is there, just there. So here OH is above, so epoxide would be above. So simply you can tick this, the answer would be B. And here with base no such reaction would be possible because both are in the same phase, and OH minus cannot just do the SN2 reaction for this type of, if both the living group and the nucleophile are in the same plane, because for the SN2 again we need to have this kind of anti-configuration to have an attack, but for this kind of cases they are in the same plane, so it is not possible for C and D. So let's so that's why B would be the answer. But for this kind of cases, so just I am not writing the whole thing, just I am choose using this particular writing this particular cyclohexane ring. So it is above. Anyway, above, here it is below, here it is below. This is one of the forms. And another form would be methyl above, here like this, but they need to be like that way. So it would be as here the ring is there, so it would be kind of puckered thing here. Yeah, the point I want to make here is with base we apply heat. So there are some interesting transformation can be possible if let's let's say this kind of thing exists. So this ring is there, and this kind of ring would be the one of the stable form. So when base we do, so O minus would be forming, and now you have two possibilities of replacing this molecule. Because same side attack is not possible, so SN2 is not an option with the O minus. So what it can do, it can migrate this hydride atom and it can remove this, or this carbon atom can be migrated and attack it, because the yeah, so this anti thing is there. So it's same side approach. So maximum thing we can achieve with this, it would be a formation of keto, nothing more than that. And for this case, so ethyl is above, below, here we is above, and it is like sorry, like this. So like this. So now if we do that same thing, base and heat, now here you can see the ring can migrate also and do this particular elimination, and it would be generating. So one of the interesting scaffold, I think, because you can see this contraction of the ring is there, and it generates a five-member thing. So it would generate this five-member ring, and it is connected to this. So it would be like this. So this particular type thing is formed if we do the base base treatment with heating condition, and here the thing would be this. So with base treatment and heat, probably very much heating condition would be needed, and the product formation would be in the less amount, but these two formation are interesting. Yes, that's why I have this. But yeah, for the simple epoxide formation, your answer should be B. So moving forward again, next question with butyl lithium and this particular thing. So again you can see this hydrogen is there. It is the acidic hydrogen because it is connected to a sp hybridized carbon. Then that's why the conjugate base after abstraction or proton have some kind of stability over other things. So that's why it is acidic in nature, and only butyl lithium means very much strong base. The lithiated species can only abstract this proton, because normal base like, let's say, sodium hydroxide, potassium hydroxide, they are not capable of doing that. Only very much this type of lithiated species, butyl lithium, tertiary butyl lithium, they can do that, or maximum so in H2 minus kind of species also can do that, but not lesser than that. So very much basic thing would be required for abstraction of this kind of protons. So after abstraction of for proton with butyl lithium, the formed species would be like this, and then they are doing this much. Okay, so write the substrate. So it's like this, followed by OTBS, this protecting group, and BF3 thread, not OET, it would be 82. It is a Lewis base. So when we apply that, so this epoxide, it actually make a complex like this, and this kind of thing is generated, so that this particular center uh, uh, became very much electrophilic. As you can see, the somewhat positive charge is over an electrophile or electronegative atom, so which this kind of molecule doesn't like, so that's want to get neutralized, and the possible way to getting neutralized is this kind of thing. So two possibilities are there, this or this. So if this kind of thing opens up, it would be a SN1 reaction. So for that case, if you have a very much weak nucleophile, then only the SN1 you can think of. But here you can see very much strong nucleophile is present. So just do the SN2 thing. So if we do the SN2 now, you would be generating this kind of species O and BF3, and it can be neutralized during O workup, not neutralized, just quenched. So protonation can become, because OBF3 minus this kind of species easily decomposes to its hydroxide form. And here we have below thing, and here the triple bond and CTMS. So this should be something you are looking for. So they actually write in this way. So just do the what to say, the RS nomenclature actually. So 1, 2, 3. So this kind of approach, and with, so what is that yes, and here if we do, it would be yes. So it matches with A, and A would be your right answer, because here if we do that, as it is so R, you would get just an enantiomer of that, which is not right. And what is this? So here you can see it may, here they attacked, oh, this particular tertiary center they chooses. If this attack possible, then only this kind of CH2H species formation is there. But you can see the SN2 is not possible, because it is tertiary center and very much bulk is there. OTBS is already a very much bulky group with methyl, so OTBS, I think you know. OTBS group is this. So dimethyl, sorry, tertiary butyl with dimethyl silicate, this kind of thing, which is very much bulkier. So attack from this side is absolutely impossible, and the only thing is possible would be formation of A compound. And yeah, the H3O plus. So just as I am saying, to just leave this kind of opponent species would be forming. No, so OBEF3 or OPOH kind of thing is there. So just to quench or to protonate that, we need just acidic workup, nothing more than that. So that's why we answer will be A. So now this thing. Again you can see with base they are asking what can be the possible product. So actually these are the classic examples for the Peterson modification type reaction. So Peterson modification have two varieties actually. So Si this kind of OH and silicon species is there, and one of the treatment you can do with base. So sodium hydride it can act as base, or you can do acid treatment. So if we do that, so that too would generate two different products. So that's the bottom line for this type of Peterson olefination reaction. So let's see. So this is our species three, and with base we all know the proton would be abstracted from hydroxide and it will become O minus. Now this O minus would oxygen silicon bond, you all know the quite uh, affinity of this of the silicon species to form a bond with the electronegative atom. So that's why this formation of oxygen silicon bond is very much facile, because silicon wants to are very much labile to form bond to uh, electrophilic atom. So with O minus it forms bond, and to break that we need more very much more electronegative atom from oxygen, which is fluoride minus. So let's say, so OTBS, just in the previous uh, question we faced OTBS group. So it is just a protecting group, right? So how it is formed with this kind of species, from this kind of species actually, not CH3, CME3, methyl. This is the reagent, the TBSCl reagent for the protection, and here imidazole, the base imidazole can be used, and this can do the protection. So here you can see again, one electronegative atom is there, which is chloride. So chloride is removed because electronegativity of oxygen is very much higher. So this kind of thing is formed. Now when we need to do the deprotection, what we use? We just use this kind of thing. So not TBA, tertiary butyl ammonium. So tertiary butyl, this kind of species we actually use TBA, tertiary butyl ammonium fluoride to, so there F minus is there and it can break the oxygen silicon bond. So now here again need to try to form a oxygen silicon bond, because no other species is there. So now we need to do the rotation to form the oxygen silicon bond. So when we do the rotation, this R1 R2 would come in this fashion, and this kind of thing would be forming. Now after that, to do just this elimination, and it would be forming this. And here this kind of species may be forming something like this, and we have generated an olefin where the stereochemistry would be E stereochemistry. So now just search for that this option, and it would be a right option. And how we can do that? Actually, for that we need some acidic source. So if we use acidic source only, then we can do this kind of anti-elimination and form the Z bond. Oh, sorry, here I have written the wrong. So it is Z actually, and if anti, it would be E. So it is Z, it is Z. So if E we want to form, then we can use the acidic source. So, and epoxide, it cannot be formed like that. So SiMe3 not that much easy, or it can not be acting as a living group. Not just this kind of attack is not possible, and it cannot generate this kind of epoxides. Yeah, look at just acidic source they are using, and it is the same substrate. It is just Peterson olefination, so related to the previous one itself. So if we use these, and here now we are using H2SO, very much acidic source, right? So the way it should get protonated like this. So after protonation, what would be happening? Just so H2O is there. So something you can think of, the oxygen silicon bond is forming, and it would help to do the this kind of elimination. And now we generate a E stereochemistry. E. So now the answer will be so like this actually. The elimination can happen, and for the previous case it was like this. Here actually one thing I need to clarify. So when this type of thing forms, there are two ways to for the elimination. Yeah, product would be Z, no issue with that. But how it is removing, that's just I'm giving just overview of that. So this kind of thing should be there, not the reverse one. So this kind of elimination is occurring to this. It is one of the path you can say. Another path would be when it is attacking. So let me write. So this is formed. So this can be formed. So here you have generated a negative atom, and here you have generated OSI. Now it is going to leave, and it will generate this one. So this should be the byproduct, but there can be two pathway. One just directly elimination like this, and another just stepwise elimination. Any of them can be occurring, but the bottom line would be formation of Z product. And here the one established mechanism is just this simple elimination, which would form a E product. Now this one. Second, PTSA, toluene sulfonic acid. Just this kind of species, I guess. So just it is a proton source, uh, just a proton source. The H plus is acidic one, and here you can see they just told with each domain means they want to know after elimination of water in presence of this what would be your product. So very much easier question. Yeah, so I hope all of you got it. Anyway, I am going to solve. Yeah, so PTSA is this particular reagent, and it is actually source of this H plus, and for this kind of molecule, these particular hydroxy groups are would be protonated. So there would be two possibilities of these and formation of the other enantiomer, which is now after elimination you would generate olefins actually. This should be one of your olefin and another will be this. So these two are actually homomers because if you do the 180-degree rotation, the double bond would came in the side this side, and we should go to the below. So one enantiomer would be forming for these particular cases, and so what I mean by this cases because this is a C2 symmetric molecule. You can easily see on C2 axis you can be thinking between this. So with that it is interchangeable, and for that case if you do the one operation in the in one of the side, so and other operation in this side, so both of them them actually are doing the same thing, and it would generate two homomers. So this is the things about the C2 symmetric molecule. So now if we match with the available options, A would be matching with this one, and B cannot be formed because here if we want to keep OH over here, it would be below one, not above one, and oxide formation over here kind of tricky, I would say, over this elimination type reaction. So that's why the most appropriate answer would be A. And again, when are using this kind of PTSA, uh, this carbocation type things is at first generated, followed by elimination, which would generate the olefin moiety. So moving forward for this kind of case, so HNO2, right? So let's see if we have primary amine and HNO2 is this source for this class thing. So this kind of mechanism operates, and it is done very much acidic condition. So that's why formation of this kind of thing is there. This kind of species is generated. Now this CO2 is present, and it can actually act as the neighboring group participation type of thing. So now just write uh, respecting your stereochemistry, that is given, which is above, and here it is. Or living group, you just can say. Now this oxygen can attack like this and remove that atom. The So in this way it generates. So here first SN2 attack is happening. So first SN2 attack. So after first SN2 attack, inversion would be there. So let's do it like that. So it is 1 2 3. So it is S. So after first attack, first is SN2 attack. Uh, stereochemistry just get reversed due to first SN2 attack, and after that only this oxide would this other acid group can attack and make this 5-member ring. uh, so it is just principle of neighboring group participation chemistry. So 2 times inversion is just equivalent of retention. So 2 times inversion is happening, so which is just uh, which is just converting, or you can say which is just uh, retention of the stereochemistry. So now here, as it is stereochemistry in the product, sorry, in the starting material. So after 2 SN2 attack, the stereochemistry would be same, and it would be, that's how you can explain, it would be big S. Moving to the next problem, so they are using two equivalent of LHMDS. And forming this. Okay, so first LHMDS, this base should abstract from the hydroxide, make it O minus, followed by abstraction of this particular alpha, any of the alpha protons. So let's see, the first enolate is generated like this. And they are saying next left while would be approaching some ways to minimize the interactions between these, and it's supposed to be a below one, so that's why they just write it below the face. Now we just need to do the nomenclature. So now numbering is 1, 2, 3, 4, because hydroxide is 2 or closer if we number from that. And first this S orientation would be there, and it would be S center, and for this case it would be so here H is above. Now this versus this should win, and this. So now this priority would be higher than this. So this this like way, but lowest priority group hydrogen is in the above, so it would be up. So 2 is, sorry, 2R, 3S. Here it is. So just like that you can do the nomenclature and solve this. So white is the other one, and if you have any query you can ask. So moving to the next problem. So they are asking this particular transformation in which class they stand. So first is diastereoselective desymmetrization and non-selective or esterification or none of them. So definitely not a esterification, because here what are we doing? Just doing the hydrolysis of this CO2 group and making it CO2. So this particular molecule, you can see this two CH2CO2 is CH2CO2. So both things are the same. So it is, that's why it is a achiral molecule. No chiral center is there. But when we just make one of the ester hydrolyzed, it would generate a chiral molecule. So one would be R and another would be S, but definitely a chiral molecule. So in normal condition, if we do this kind of hydrolysis, you would generate a racemic compound, as stereochemistry of this center cannot be fixed because it is a chiral molecule anyway. So you need to do a enantioselective desymmetrization for this kind of transformation. So that's why right answer would be B, because the stereoselective. So the what would be the other enantiomer? So let's see. Here we are doing hydrolysis. So this definitely be one, and another would be here star group would be remaining, and let's say here we got the hydrolyzed acid. So this should be the other isomer, and if you do the relations assignment between these two, this should be enantiomers, because anyway it contains just one chiral center. So that's why it would be enantiomer selective desymmetrization. So now you can see this kind of so if we use general condition, we cannot get any enantiomeric excess, because it is an chiral molecule and we are doing hydrolysis. How we can make one of the particular enantiomer in excess? So that's why the many papers are there. So here just a quick view of this kind of things. So let's say if you have this kind of molecule, so it is, you can just pass a sigma plane between this uh, containing this three carbon, and it would be the sigma plane. So that's why it would be a chiral molecule. Now if you just convert one of the alcohol group to any of its functionality, to make this OH and this OH different. So just do the appel reaction. It would make a halide over here, and here and another side would be unreacted. Then it would be a chiral molecule. So any monofunctionalization would lead to making of a chiral molecule from a chiral molecule. But in the previous problem you have seen, so that should definitely be generating a racemic mixture, because with general condition we cannot control that. So for that there are various catalysts are developed to generate one of the particular enantiomer as the major one. So here is some of the examples. So here you can see zinc based catalyst, where zinc is attached to this kind of ligand. Here you can see, and with this ligand they have achieved up to 99% enantiomeric excess, sorry, 93% enantiomeric excess, and this particular thing is the yield. So maximum yield they have called 99, and enantiomeric excess they maximize to 93%. Another thing is this chiral DMAP based catalyst. Here they can achieve up to 90% enantiomeric excess, and here with this simple this kind of molecule, it can you can go up to 67% enantiomeric excess. So how they work actually? So for that in this paper I have just seen and thought of incorporating that. So in JAX 2021, this particular research is published. So here you can see this achiral molecule having the sigma plane, and they want to do one monofunctionalization to make this molecule asymmetric. So this kind of borane based reagent they have used, which so when they use this kind of catalyst, borane based, and with two dihydroxy compound, it would generate this type of borates in situ, followed by their attack with this kind of this kind of electrophilic system, and they just make this molecule with up to 96% or 92% enantiomeric excess. So it is enantiomeric ratio 96 is to 4. So one of the enantiomer is excess up to 92. So that's how you can calculate. So here they have proposed a model how one of the enantiomer is they are making in major amount over another. So this is their catalyst. Here you can see this is the substrate that we are using. This phenyl and proton are the two substituents. So here you can see AR is normal phenyl group, and proton is already present here, and CH2H which are this. So when you use this type of boron based species, so oxygen boron bond would be forming, and this would generate this kind of molecule. So when this particular transition state is formed, so this particular BO oxygen boron, so this particular thing would act as nucleophile, and nucleophile they are using is this particular PHCH2X. So X is halide, bromine, iodine, anything can be possible. And in the catalyst you can see here uh, so this kind of thing is there. So it would generate a you can say chiral bond. So this particular chirality is present, and they are so binary based systems you can actually see this kind of chirality. And here you can see this this OCPH due to is very much bulkier group. So this particular group is actually responsible to block one of the sites. So if this molecule can want to approach the electrophilic center from this site, it is not possible due to presence of this huge bulkier group, and this particular site would be free. So that's how the enantiomeric excess they have got, and that's how this particular model works. And here they are this particular atrop isomer they are using. So two isomer would be possible, right? So okay, one is this and another would be that side, just flip it. But due to this steric hindrance, this particular rotation is hindered, and so that's why this particular isomer is fixed in this particular form. So this kind of compounds, they are atrop isomers actually, and this particular one of the atrop isomer they have used to have the to make uh, this molecule stereo selective way, and they have achieved up to this 92% enantiomeric excess. So this particular concept is regarding this enantiomeric desymmetrization. So in that way you can this particular catalyst can control this enantiomeric ratio. Coming to the next problem. So in this particular synthesis, we will disconnect the molecule. So now if we disconnect these two, so it would generate, let's see. If we disconnect between these, this is pH. So let's consider this particular aldehyde molecule we are disconnecting with. Another would be this. So yeah, hydrogen would be. So these two hubs we are generating. So all things are the same. Now just chiral center is there. So now just we need to assign the chiral center and check if these two are homomers or enantiomers. That just they are asking. So it is R here which is below. It is also R. So we are generating just two homomers actually. We are generating and so now let's look at so two heterochiral hubs. So they are not heterochiral. They are just homomers. So this one two homochiral molecule because both rotation or both configuration is R and molecule is C2 symmetry. Of course, you can obviously consider a C2 axis over this plane or these two bonds. Between these two bonds, you can think of this C2 because if you rotate 180, it would just generate or just generate the same molecule and that's how you determine this kind of axis. Due to and molecule having a symmetric plane. So now look at if it had a sigma plane. So sigma plane cannot be passed over this plane because one side you will see which is below and another side it is above. So sigma plane cannot be passed between these two. So C you can eliminate. So the right answer would be B. So and the previous probably the TSA case we have discussed. Yeah, so here we also have a C2 symmetric molecule and we generate two homochiral molecules. Here it is just related to that only. So here also we have C2 symmetry and we generate two identical halves. So when you have this particular C2 symmetric molecule and you just always it is actually fact that any of the side, let's say here you want to desymmetrize and here you want to desymmetrize anywhere you do it would generate homochiral molecule. So it is also true for when you do the disconnection. There also it is this law is holding that you don't generate two halves where the molecule would be homochiral. So that's thumb you can say a thumb rule for this kind of C2 symmetric molecules. So moving forward for the next one. So there are quite a lot of molecules. So just do this operation and let's so they are using it in two equivalent and it is one equivalent. Let's do the mechanism. So this kind of ways actually attack this electrophilic centers, and it would remove just the fluoride atoms. So after first attack, the fluoro would be removed, and it would generate this kind of species. So if you want to make this wedge in the plane, just do 180 rotation, and it would end up with this particular system actually. Now after second attack, same way you can attack this removal. This would lead to formation of this kind of molecule. So which is just directly matching with this. That's that way you can solve this, but another way would be do the arrest nomenclature, because when we are attacking, this center is not affected. So in this particular system also, the molecule would retain its stereochemistry or its RS nomenclature. So let's do this. It would be A. So when it is in the molecule, you just do the RS nomenclature thing, and where it would be S and S, that would be your product. So for this case, one, it is hydrogen is above, so it is S. Hydrogen is above, it is S. For this case, it is equal to R, would be R. So not right. So here would be again R, and it would be S. Now it would be S, it would be R. So here you can see this RS, SR, they are not matching with this particular thing, that your compound should have this S and S. So that's why this one would be not the correct product, and the right answer would be A. So I think 16 problems. So this assignment have only 16 problems, and so I think this this much problems I am having, and so I have one. We can discuss one total synthesis, but the time is quite low. In minutes, I cannot finish that. Let's save it for the next class. And today, if you have any question, you can ask. Any clarification, any doubts regarding the lecture series, and any of the today's problems that I have solved. If you have any doubt, you can ask. So seems like not. So just just one practical view of this particular reaction I will just want to share. So with PTSA, what are we doing? We are eliminating H2O, and we are kind of generating a carbocation over here. So this particular conversion would be reversible, let's say, because we need to do elimination, and when carbocation is generated, H2O always can attack this and regenerate this kind of molecule. So let's say when we generate this kind of carbocationic species, H2O is there, it always can attack this particular carbocation, and it may lead to this or this to diastereomer can be easily be forming with attack of this. So this kind of elimination is kind of reversible in nature, because it always prone to degenerate dialcohol molecule. So for the practical overview, what we need to do when we do this kind of reaction, so there is a setup called Dean stack. So in this particular Dean stack setup, so here you have your reaction. Let's say you are doing reaction over here, and heating condition is needed for this kind of cases. You are doing reaction PTSA, and your solvent is there. Now for this kind of arrangement, there is a setup like this way kind of thing. So here what is there? So let's say you are using here toluene. So toluene would be filled up to this point. So it's quite bent actually. That's why it would not directly pour, but it would remain in this particular fashion. But when you are heating, so let's say you are heating above 100 degrees Celsius, because it kind of condensation, reflux, sorry, not condensation, reflux condition, at toluene boiling point is 110. So now when around 100 degree, when H2O is removed, it would be like this, and between H2 and toluene, which is have higher density, H2, because organic phase, I think all of you do the workup. So organic phase like toluene, ethyl acetate remain in above layer, and water is in the below layer. So that's why when water comes, it directly comes to the below, and it would be collecting over this particular center or particular area. That's how H2 is removed, and it is stopped from coming to the reaction vessel again. So that's how you can make this particular arrow as not reversible, just irreversible by this kind of particular gene stack setup. So that's the thing we need to maintain for this kind of reaction. So it's just a practical view of this, and now I think there are no more questions. We can just conclude today's session, and thank you for joining, and we will be meeting in the next class for the 12th live session. And thank you all for joining. We'll meet same time 6 to 8 in the next next meeting. So thank you.